Welcome back, guys. Day 10. Right, we got atomic spectroscopy and the Bohr model. Alright, so atomic line spectra. Or sometimes as we call them, emission spectra, right, are always the same for each individual element. Right, and this is similar to a fingerprint. Alright, so if we look, I have some emission, like here's how this works. Hydrogen lamp, and that's basically the color, it comes through a slit and then a prism separates it into 4 different colors. If you had a helium lamp, you would see something like this. A barium lamp is something like that. A lot more lines. Obviously the sun, white light spectrum is all the colors. So what hydrogen is it breaks into 4 colors. A purple that I can barely see, which is 410 nanometers. A more of a blue, looks purple to me, of 434 nanometers. A more teal color of blue-green of 486. And then more of a red at 657 or 656. Right? And so that's what we observe for this. Okay? All right? And you can see Bohr's result, his predicted result is what's going on here, and we'll talk about that. We'll expand on that in a moment. So in 1913, Bohr came up with 1913. Niels Bohr came up with this theory, and he said the angular momentum. Well, what is angular momentum? Well, we have momentum, and we're going to have angular momentum. So momentum, of course, is mass times velocity. Right? Mass times velocity is momentum. So if you are moving really, really fast with not a lot of mass, or you can be really, really big with a little bit of mass. Right? So, but mass times speed is momentum. This is why they say trains, it's harder to stop. Even cars going faster. The faster you're going in a car, the harder it is to stop because you have more momentum. Now, angular momentum would be in a radius, right? Going around a circle. Right? So the angular momentum of an electron in a hydrogen atom, right, is quantized, which means it's restricted in its allowed values, which means we can't be anything. All right, we just can't be any value we want, and this equals N, which will be our energy level, H over 2 pi for the circle. All right, so this means the electron, so N is the energy level. Let me define that. H, of course, is 6.626 times 10 to the negative 34 joules times seconds. Planck's constant. All right. So the electrons are only allowed in certain orbits. All right, so we're only allowed in certain orbits, and that's okay. Right? So a good way to think about this is if we're going up a building, you could have stairs, or there could be a ramp. Right? Stairs versus a ramp. Well, on the stairs, I had to be on step, I guess 1, 2, 3, 4, 5, or 6. I have to be on a stair. I can't be floating between stairs. I can go from stair to stair. I could jump 2 stairs, right? And kids, the big deal is when they first get going, they go down the stairs, they can jump the last stairs. Then they do 2 stairs, and then they do 3 stairs, and then they do 4 stairs, and they're just jumping, and they're getting kind of dangerous, right? I know I did. I know my kids did. Sometimes they still do, right, for fun, right? So you can jump from this stair 5 to stair 3, no problem. But you can't be hovering at stair 4.5. You can't be just hovering in between. That would be weird. If you were going up or down stairs and you look and somebody's just hovering between the stairs, that would probably freak you out. And I would understand that's probably a good idea to be freaked out there. Right? The ramp, however, we can be anywhere on this ramp. I can be anywhere. So the ramp is what we call continuous. So this is continuous, where the stairs are quantized because there are only certain values. Now you can go between the values, but there's only certain values. All right, hopefully that kind of makes sense, that you can't just be anywhere. Well, the energy of an electron in an orbit can be represented by En equals negative RHc all over n squared. Well, R is a new number. R is the Rydberg constant, so which is 1.097 times 10 to negative 1 meters. I'm sorry, 10 to the 7th. Meters negative 1. Meters is on the bottom. Or 109,768. Same number, wave numbers, right? And by the way, centimeters negative 1 is a wave number, which is 1 over centimeters, which we also use that for. It's a wave number. Okay? All right? And so our lines, this is the key point. Lines, spell right. Lines in an emission spectra. Right? So in the line in the emission spectra, or the line spectra, all right, are due to the transition of an electron from a higher level to a lower level. Okay? And the transition would be delta E, right, equals RHc 1 over N minus 1 over N. Now these N's are both going to be squared. Well, let me use orange down here. So this would be N1, or the initial, N2 is the final. And they're both going to be squared. All right. R is R, H, that we just talked about, the 1.097 times 10 to the 7th per meter. H is Planck's constant, C is the speed of light. Delta E is the change in energy. That energy is what we see, right? Because remember, a little side note, E equals HC over nu. So this delta E can be put into this equation right here and get the color out, right? So what Bohr noticed is that You had 410, 434, 46, and 657. These nanometers here. They all represent an energy. That makes sense? They will represent the difference between these energy levels. And we found out to be 2 to 6, 2 to 5, 2 to 4, and 2 to 3. Or 6 to 2, 5 to 2, 4 to 2, 3 to 2. All right? Now, 3 to 1 exists, 2 to 1 exists, 4 to 1 exists, 5 to 1, 6 to 1. They all exist. We can't see them. They're in the UV. We can't see them. We can only see these four for hydrogen. There's more for helium you can see. There's more for barium you can see. But these are the transitions that we can see. So let's do a quick example here. Let's do a quick example. What is the wavelength? Of light. What's the wavelength of light for the emission when the electron travels or moves from n equals 3 to n equals 2 in the hydrogen atom? All right, so that's what we're going to do real quick. So, delta E is what we're looking for, kind of, equals R 1.097 times 10 to the 7th, 1 over meters. H 6.626 times 10 to the negative 34 joules times seconds. 3.00 times 10 to the 8th meters per second. All right, so now we have the n's. And just to recap, can energy be negative? No, right? Just like money is not negative. Well, I can owe money, yeah, but it's still money and it still has a value. $20 is $20. It has nothing to do with, the actual value. It has to do with direction. So positive $20 means $20 coming in. Negative $20 means $20 going out. Positive energy means energy's coming in. Negative energy, energy going out. All right? So it doesn't matter which way you do this, if that makes sense to you. Because delta E, when we put it into this equation up here, if you can see the mouse, right? This equation up here, we will need a positive energy for it anyway, because you can't get a negative distance, right? That is not going to happen. Okay, so N1 would be 3, and N2 would be 2, but it doesn't matter what you do, all right? Because the difference is going to be the difference. Okay. Let's put this in the calculator and solve. So how do we do that? Well, R is 1.097 times 10 to the 7th times 6.626 times 10 to the negative 34 times 3e8. Open up my parentheses. I have 1 divided by 3 squared minus 1 divided by 2 squared. Close my parentheses. That's all I'm doing. And I get 3.03 times 10 to the negative 19 joules. Now, this negative sign just means that it is energy out. Right? So delta E now, so that delta E, which is E, which is HC over lambda. And if you remember from before, multiply both sides by lambda, divide both sides by E. Lambda equals HC over E. So lambda equals 6.626 times 10 to the negative 34 joules times seconds. And some of you right now might be realizing, well, H and C are in both. You could, if you wanted to, set these things equal to each other and do some algebra. You're more than welcome to do so. I'm not going to, because the vast majority of my Chem 1 students do not have any desire to do that. All right, we got 3.00 times 10 to the 8th meters per second, all over 3.03 times 10 to the negative 19 joules. Now, calculator. 6.626 times 10 to the negative 34 times 3 E8 divide. I'm just going to throw in second answer. Now I'm going to do that. It's going to be negative. Obviously my answer is not negative. It's positive 6.56 times 10 to the negative 7th. So that means my wavelength is 6.56 times 10 to the negative 7th meters, which is the same thing as 656 times 10 to the negative 9 meters, or 656 nanometers. And that's what we should have got. All right, that's what we get. Okay, 656, 657, I'm happy. So this is a very good math problem we did. So again, when we talk about science and models, we want to make sure that our model behavior from our math equation, whatever we're doing, our calculations, mimic our observed behavior. So our observed behavior is that we see a red line at 657 or 656 nanometers. Right? And if we were actually on campus in lab doing this, we actually do this experiment where you look at the hydrogen lab with a device, a tool, that you can actually see these colors. It doesn't, the scale's off on them because they're not the most expensive, but you actually see that. We have a really nice $1,000 one that we use, and we show you that, yep, that's the actual wavelength. We actually show it to you. And so it's quite nice to see. And you can see the different lamps have different ones. It's actually a very nice qualitative lab. All right, and so our model matches our observations, which I really like as a scientist, right? This is why I would not be a good weatherman, because my model doesn't always match what's observed. I'm not trying to pick on them, but that just happens a lot. So here we want our model to match observed behavior, and that's really good. All right. So Bohr came up with his planetary model of the atom. And so if we look at this again, you got the nucleus, that's the sun, and then you get the electrons going around these orbits. All right, and the different transitions are the colors we see. It's a great model. It's a great first model. There are problems with the model, though, right? And I think we skipped the fact that Rutherford did his gold foil experiment and found that the nucleus of the atom, and that there's a nucleus and there's a lot of empty space. Problems with Bohr's theory here. Now Bohr did a huge work, all right, but he did not know that electrons do not move in fixed orbits like planets around the sun. Don't do that. Also, this works for one electron systems, which is a very nice way of saying it only works for the hydrogen atom. So that's 1 out of 118. Not bad. All right. So, and again, this is amazing. He's done much better scientist than I ever would hope to be. He's brilliant. All right. And what it did, which is a huge step forward, right? Big step forward, is that he did introduce the quantization of electron energies, and explain the H atom line spectra. This was huge. This was absolutely huge. So that was Bohr and Bohr's contribution. One of his contributions.